In this video, I want to talk about programming assignments in my classes and how I think you should approach them if you want the greatest return in points for your investment of time and effort. So to begin, let's look at what I emphasize when I am grading. So the very first thing I encounter when I get your code is I'm going to try to compile it, and it either successfully compiles for my target environment or it doesn't. And code that doesn't compile, no matter how many hundreds or thousands of lines big it is or how many hours of effort it represents, is 100% worthless to me. You will get no points whatsoever for code that does not compile. Compiling with warnings is okay-ish. It is by no means great. And you should expect to lose some points if you compile with warnings. But it's way, way better, infinitely better than not being able to compile at all. Now, the test environment that I'll be using will be some form of Linux, typically the Ubuntu distribution, and it'll be pretty up-to-date, usually the most recent long-term service version. So you can set yourself up a virtual machine with whatever that happens to be at the moment, whatever version that happens to be at the moment. And then you can do the testing with the same environment I'll be working with. And I'm going to use two compilers for everybody's programs. And right now we're just assuming that these programs are written in C or C++, but obviously depending on the course you're taking, it may be something else. So for the C and C++ world, I'm going to be using GCC, and then I'll be using Clang, which comes with as a part of the LLVM suite of tools. And if you're a Mac user, you already have via Xcode the Clang compiler, and you will have, if you use the Xcode command line tools installer, you will have wrappers for Clang that purport to be GCC, but they are not. So if you want to test on GCC and you're on Mac, either through Homebrew or Fink or something like that, get yourself an actual GCC installation up and going. Or again, consider setting up a virtual machine, installing the latest long-term service Ubuntu version, and then get GCC and Clang on those, and you can test your systems there. Now with GCC, and Clang as well, really, there are a couple switches that you should use, and I've got them listed here on the slide. The first of these is the -W all, and this sets the warning level to be high. It's a little misleading though, because it suggests that it will show all warnings, and that's not quite true. But it does put the warning level quite high, or at least higher than normal. I'm also going to set the warning level to pedantic mode. So a lot of compilers are getting pickier and pickier about things, particularly the use of functions that are known to be very unsafe. And so by putting this thing in pedantic mode, we're going to get even more complaints than just saying all, setting the warning level to all. Right? So at least these two is what you should use. They're the two that I'll be using just so that I can nail down some different things and give you some feedback. So if you can't deal with your warnings, but it still compiles, this is okay. You know, submit it if you must, and then I'll try to help you to isolate what could be done to get rid of those warnings, other than suppressing particular warnings with compiler flags, because I don't think that's ever a good idea. All right, the second thing I've got bulleted here is that something is often better than nothing. Now I say something is often better because sometimes students get creative in the way they try to sort of give me something that compiles, or there is at least some kind of activity happening. But if it's not really related to what I asked you to do, it's worthless. But the key here is that in any assignment, there are going to be very specific things that you need to do. Now there will be trickier calculations, and there'll be simpler outputs and simpler inputs than some of the trickier calculations. But every little piece of that can be demonstrable if you make it exist. So don't get hung up on, I'm trying to do the first big piece of a program and I haven't gotten it to input this strange thing that he's asked for yet, and so I can't move forward with the rest of the program. You could always potentially do things like stub that out, have the program pretend that it got some input by assigning some default values. You could even report this to me at runtime by having a nice bit of text print out that tells me what's going on. Don't just put stuff in comments in your code, because I won't look at that first. I'm going to compile your program and run it. So make your program tell me things like you didn't get the I/O working yet, and so you are stubbing it with some particular piece of data, like you're going to interpret each of the 27 values I told you to read in as a 5 or something, just so that you can move ahead. That way you've got more than nothing, and because it's helping you to get things done, I'll appreciate it more. So something is very often better than nothing. But whatever work you do, make sure that you're gearing it towards something that is demoable. And not because you can come to my office and show it to me, but because I will compile your code and run it. It must demonstrate itself then, and then it's probably going to be worth something. All right, similarly, I'm looking for evidence of planning and decomposition. So decomposition is when you take a large problem like a programming assignment, and I'll give an example of one at the end of this video. You take a large assignment and you break it down into a bunch of little pieces that all need to get done, something like a to-do list. Right? What I want to see is that you've taken the time to break that kind of thing down. So if the whole program, if you've got it perfect, if everything works great, then this isn't going to be something I'm going to be investigating very deeply. But not every program submission is worth 100%. And so when it isn't, I want to look for how did you break the big problem up into smaller pieces, and how many of those small pieces work perfectly. Right? So it might be things like printing out prompts. It might be things like formatting the output, both of which are extremely trivial, and so they ought to be done well. But you can easily separate those out from the larger problem, get them done right away, and then you've earned yourself some points. Right? I want to see that you've thought through, like, this will happen, this will happen, this will happen, this will happen, and you've taken chunks like that and made those individual chunks completely done. Some of the worst programs, in my opinion, and I'm the one doing the evaluation, in my opinion, some of the worst programs come to me and they try to do a little bit of all the parts of a program, but almost all of them don't really work right at large. They work for just one very simple type of example, and then each part fails when you start manipulating whatever the input data might be. These are miserable programs. I want to see pieces of this stuff that are rock solid, so that it appears that before you submitted this, you sat down, you thought about the problem, and you said, it's this, 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 and this. And then you said, well, this one's easy, so I'll make that happen. And this one's easy, so I'll make that happen. And this is the next easiest, and I'll get that to happen. And some of these others, because I've run out of time, I've stubbed. And then you'll report to me through some printout at the top of your program execution that you've done this kind of stubbing. And I'll say, now there's somebody, even though they didn't get done, who's made a plan and saw it through as best they could. And that will earn you points. Not because I want to reward people who just make plans rather than get these small homework assignments done, but because I want to prepare you for a life of engineering where problems are really large and you just cannot sit down and tear these things out. We have to think, we have to break the problems down into smaller problems that we can solve individually and maybe abstract away or encapsulate in functions or methods or some kind of unit, right? All right, correctness is important. So I want your program to work correctly, to have good formatting and everything like that. And when I provide it unusual data, I want it to produce exactly the right result. That's all very important. However, I respect the fact that you are learning. So I don't want you to feel as if when you're doing this kind of development, if you encounter bugs, which will happen quite naturally, that you are tanking your grade or something. Instead, I want you to see this as just another part of your problem. So you've got something working, great. If you've got bugs, we want to correct them, and I'm going to give you some advice on ways you might go about that in a general fashion. But sooner or later in one of these programs, you're going to get stuck on something and you just don't know why it isn't working. Don't stress out over that. If you decomposed your problem into all these different little constituent parts, and you're stuck on some bug here, and it's partly working and partly not, I say here that bug tracking is also important. When you're submitting a program to me, have the beginning of that program print out some details about what I should expect to see if it isn't perfect. So tell me something like, this works great for even numbers above 28. Not that that's a totally reasonable type of bug to have, but if that's the best that you've got, you figured out from a few tests that certain types of data work fine, and here is some details about the data that doesn't, let me know so that I can expect that data to fail. In fact, I'll even prefer to do a test where I try that kind of data and see that you are correct, that it actually fails. That means you've provided me insight into what you're doing and that you are paying attention to what your program is doing correctly and what it is doing incorrectly. So don't just focus on everything being perfect. We have time limits to get things done, and when we get into huge pieces of software in our lives, products must roll out, even if there are known defects. We just have to be honest about the defects and make our users aware of them as best we can until we can deal with them. Right? So do the same for me. Formatting is absolutely essential. So formatting, being just what I say, is nearly as important as the code compiling. If it's not formatted just as I say, you won't get a 0. But I am going to be so irritated that you didn't do something so simple as capitalize the first letter of that prompt just like I did, and then use a colon with no white space just like I did. Don't give me your interpretation of the exact output that I provide you. It will only infuriate me that you couldn't follow the simplest part of the spec of our program. Now maybe that seems pedantic, but as we go out in life and have to write software that doesn't kill people or helps people stay alive, whatever it may be, or works with our finances, I think it's dreadfully important that we do it to spec. So when I say here's what a thing looks like, yours ought to look just like it. I ought to feel like running your program is really close to running my program. Right? So that's the way I want to see it. Now I've got 2 other notes down here in red. The first is once you, and these relate to when you think you're basically done. So once you're done with a program, before you submit it to me, I highly recommend you get access to a tool called Valgrind, another tool called ScanBuild. Now ScanBuild is part of the LLVM suite of tools, but at least on contemporary Ubuntu systems, as well as Mac systems that come preloaded with Clang, at least in the command line for Mac, you're not going to have access to the ScanBuild application, so you're going to need to acquire those some other way. For an Ubuntu distribution, which is based on Debian, the name of the package is clang-tools, and that will give you a program called ScanBuild. I'm not going to go through how to use it here, but basically that's a static analyzer, and it will help you find all kinds of potential defects that may exist in your software without even having to run the software. It does it just through compiling. It's not foolproof, it doesn't find every bug, and some of the bugs that it reports aren't really bugs, and you'll have to use your massive brain to figure out which of those situations it is if it decides to report something to you. But it definitely helps before you send this thing off to have some kind of a tool that can at least give you the sensation that there is some quality there. Now, Valgrind is not a static analyzer. It actually requires running your program for it to give you any valuable feedback. But it'll do things like test for memory leaks. So if you take your program, and let's say you're compiling with GCC, if you add debug symbols by using the -G flag at the time you compile, then when you go to run this thing, instead of, say, let's say your program is called, I don't know, program 1. If you would normally run that by saying /program1, then now you'll run it by saying valgrind space /program1. So whatever you would normally type, you just put valgrind in the front and a space. Valgrind will then work as a shell, much like the terminal that you're running your programs in the first place. And when it runs your program, it's going to do some stuff with the memory space that your program is loaded into, so that it can detect when you are manipulating that memory, writing and reading. And if you've got the -G flag in there, it's also going to be able to correlate this to the actual code that's executing. So instead of just saying your program has read from some memory address or written to some memory address, it's going to have some insight into the structure of your program, including like file names and line numbers. And it will be able to tell you things like, you do a run, it looks like everything may have worked just fine for you, but it might be able to print out that on line 483 of file whatever, that you used a variable in a condition and that variable hadn't been initialized. Now, of course, you might say, but my program produced the right output and it didn't crash or anything like that. And that's neato, but it's probably an accident, right? Or a coincidence that it didn't crash and that you got the right output. So even if you're seeing everything run perfectly, if Valgrind tells you that you've got memory leaks, or it tells you that you've used some variable in a condition that wasn't initialized, or any of the other number of things that it can tell you and give you line numbers on, you'd sort of be a fool not to go to those lines of code and figure out how to correct those issues, or at least evaluate whether or not they really are issues. So I highly recommend before you submit your program to me online that you run those things. Now for my classes, whenever I create the drop boxes where you can upload your programs, I always make sure that you're able to upload as many versions as you want, so that you can get one up there just to ensure that while you're, say, traveling or something, if something were to happen to you, you wouldn't be stuck not being able to get another submission in that's better before the assignment is due. So it's totally reasonable to finish your work, upload the assignment, and then start testing it, and then if you can improve it and correct issues through the use of these tools, then upload it again as long as it's before the assignment deadline. All right. Now, those are the things I emphasize on the grades. But when you approach doing these assignments, you're going to have a couple of core problems that I see all the time in students. And I won't deny that I don't have them myself from time to time. Excuse me. But I want you to at least be aware of them ahead of time and try to get over it. So the first thing is, I don't want you to have this kind of artist's blank canvas effect. Right? When an artist is sometimes staring at a large canvas ready to do something, there's some permanence to what they may do, and so they like to think a lot about what they're going to do. And they may stare at a blank canvas for a long time before anything actually happens. And that is, generally speaking, worthless when we translate that to us sitting in front of an editor with a blank file in front of us. If you're having trouble getting started, you need to identify that right away and do something about it so that you can get something done, because we want something rather than nothing, and we want things to be demonstrable. Right? So as I mentioned before, one of the best things you can do here is start to decompose the problem. If you're not able to just start doing it, then you need to sit down and you really need to break it into, it's this piece, there's this piece, this happens next, and then this. Decompose it and actually write this down as a list. Now you don't have to write it by hand, you could type it in somewhere in a text file, or you can make comments inline in your code in your otherwise empty file. They're just like, this happens, this happens, this happens, then this happens. It's at least going to give you a guide by which to do some things. And when you see an actual list, you'll recognize which things will be the easiest to do, and then you have the potential to get those done. Now I'm going to go to an assignment for a class that I'm offering in the semester that I'm filming this, just to give us a concept. So here is some example output for a program that's supposed to deal with the input and output of numeric values in arbitrary bases, or at least somewhat arbitrary bases. So the idea is the program prompts for an input base, and then the user provides a number somewhere between 2 and 16, at least for this particular assignment that I'm using as an example. Then it prompts for an output base, and so in this example we've provided an input base of 6 and an output base of 4. Then you're going to give it a number in the original input base. But notice in this particular program, that value 6 that was given by the human as input is duplicated here as a part of the prompt, and that demonstrates that it's captured that number. Now that's not an exciting thing to have happened, but this is the idea. You can break the program down into little things and make those little things happen. So when we say what base 6 number, then we provide a number that's in base 6. Now for this program I had identified that all input will be valid. There will be no malformed input or improper input. So here is a base 6 number, and then eventually we're going to print this thing out as a base 4 number. So a couple things happen after we've gotten these 3 pieces of input. The students' programs are supposed to print out the coefficient base exponent form expression for the number in the base provided, and then say that that is equal to some value here in decimal. Right? Then using iterative integer division to capture quotients and remainders, we print out the results of each iteration of division by the target base so that we can find the remainders, which will end up becoming the coefficients in the converted base result. So once all these have happened over and over until that quotient gets to a 0, then we have the program print out its final result. So it prints out the original string entered by the user and shows what base it's in with a subscript 6 underscore 6, and says that's equal to whatever it will be after it's converted with an underscore and then the target base number. But let's decompose this very quickly into a short list of things that anyone could do right away. Now the first is, here is a series of lines of output. What input base, colon, and then yeah, we're supposed to wait for input. But you don't have to wait for input. You could just write a program that prints that prompt, and then prints the next prompt, what output base, and then prints the next prompt, what base, and then you could put an X instead of 6, X number, colon. Notice how everything's formatted, notice there's a space after the colons. Just get that output in place. Just simple printf statements. Here is something where it's supposed to put something in coefficient base exponent form. You could just print out the string coefficient base exponent form, or you could just have a comment in your code saying print out the coefficient base exponent form, something like that. Here's a header for a table that's always the same, Q space colon space R dot dot dot. Just make that get printed out. Right. So this is a simple set of things that can be done right away. What's the next easiest thing to do? Get the input base. It's just going to be some number, and then print that base out as part of that prompt where we used to say what base number, and maybe we had an X. Instead, print the actual number. This will take almost no time, and it's demonstrable, and it's shown some planning and breakdown if that's all you have in the end. Right? It's not worth a lot, but it shows you did what you could to break it down. All right, so let's go back and talk about some other stuff. All right, so we're working again, and then we hit bugs. When you hit bugs, for whatever reason, engineers, we're concerned about our stuff being correct, and so we often let a bug in that we've encountered in one part of the program grab all of our attention and prevent us from making progress on other parts of our software. I don't want to see that happen with you, so I want you to avoid this situation. There's a couple things that you can do right away. If you encounter a bug and you're not able to figure it out within some very limited period of time, say 10 minutes, right? Give yourself an actual deadline, set a timer. Now, you don't always have to set timers, but if you're discovering that you're getting into this bug business and your time is slipping away from you, set a timer. I suggest 10 minutes. If you can't resolve the bug or you don't feel you've made sufficient progress in resolving the bug on your own, however that is, then when that timer goes off, you need to try running this thing with some kind of an automated tool like Valgrind or ScanBuild. Since those tools can identify lines of code that have issues, if you see lines of code in the area that you're working on, then you can try to deal with those lines of code based on the output from these programs. If it gives you info on other lines of code that you don't think are related, you can at least see if those issues are resolvable quickly, and then test to see whether or not your bug has gone away. You may think that that seems fairly unstructured to deal with what might be bugs in other parts of the code that clearly don't have anything to do with your bug. But bugs aren't bugs because they make lots of sense. They're bugs because something is wrong. And it could be that your structure has been compromised somehow, and so it's totally reasonable to look at things that you otherwise think are unrelated. I mean, after all, most of us, when we encounter bugs, at least early in our careers, we don't find them very quickly because we're certain we wrote it right? But there's clearly a bug, so we didn't. So take my advice. When you can't get it done quickly on your own, stop working on it, use a tool to help you find something, and then deal with those issues. If the bug still is not gone, then one of the things you need to do is at least try to determine the type of input patterns or the situation in which that defect surfaces. And then, in doing that, you may suddenly go, aha, I know what is causing this, and then correct it. Great. If you can't figure out what's causing it, and so you can't correct it, but you've isolated more clearly the type of input or situation that raises the defect, then you can add to some printouts at the top of your program execution. Here are some known defects, so that when I go to evaluate your program, I'll be informed of that right away, and I can verify that such defects exist. And that's only going to improve your grade. If you had the defect and didn't report it to me, and then I discover the defect, you're going to end up with a worse grade than if you discover it and report it to me and it still is there, but with a report. I'm always going to appreciate that more because that has greater value. That mentality has greater value in the long term in big software development. Right? So report the issue and then move on. Okay, and the last thing here is that points are going to be earned through demonstrable artifacts. I don't care about how much time and effort you spend. What I care about is how many pieces of the vision of my assignment you've actually got going on. Right? So what's there, what's correct, and for the things that are there that aren't correct, did you identify them and report them to me, rather than just they're not correct and that's there. Right? That's not the same as you demonstrating to me that you are aware. So make that stuff happen. That way you're not wasting your time. And the last point here is I don't want you to actually waste your effort. So don't try to improve the feel of a program that has defects that you're aware of it, and so on. Anything extra, or even if you've got a perfect program, don't add extra stuff to it. If it's perfect, it shouldn't report anything to me because everything's going to be fine. Don't add fancier prompts, more detailed output, more step-by-step output showing me how your calculations work. I expect that if it works right, it will just do its business as I have laid it out, and then give me the results I expect. If you are trying to demonstrate for a program that isn't fully functional or fully correct, that here are the results of your partial calculations and that you're performing a particular algorithm that I described in lecture or something like that, then it's absolutely appropriate, from my perspective, to print out something at the top of your program saying, here's what isn't working. I have extra printouts to show the algorithm in process. And then I'll see it and say, this is great. At least you're giving me insight into what's going on. So that's my advice for getting the most points for your program submissions when you're working on a programming assignment in one of my classes. I hope it helps. Please remember that not all faculty are the same, and there will certainly be faculty who only want exactly what they request. I've definitely dealt with faculty who require that the program at least functions correctly in its entirety for you to earn any grade whatsoever. So don't take my advice as a compelling example to follow in all your classes, but if you're in one of mine and you follow these recommendations, you're going to get the best grade that you can for those assignments, especially when it's on an assignment that you're not able to complete perfectly in the time allotted.